Okay. Good morning. So today we'll talk about numerical differentiation and integration. And we'll start with differentiation, our way of producing methods or uh, procedures for numerical differentiation is by using a Taylor series or polynomial approximation as we know it from calculus and using and and we use the Taylor series for more than one point, and we sum these points with coefficients so that the terms that we don't care of will cancel out, and we are left with what we want. For example, the first derivative or the second derivative or whatsoever. And we can bound our error using and exploiting our knowledge from Lagrange remainder theorem and from other theorems from calculus, such as the intermediate value theorem and a mean value theorem. We will be interested here only in the order of we'll be interested only with how the error scales with h. H is the little step or the small segment that we use for our differentiation. And here is an example, the first example that we got before. We know that the real derivative is the limit when h goes to 0 of f of x plus h minus f of x over h. And we should take h to 0, but as we know, we cannot take h to 0 by using the computer. And h has some minimal value that we can take. So we can use our knowledge from calculus and say, okay, f of x plus h is f of x plus h f tag plus some error that goes as h squared, and this psi is some value between x and x plus h. Okay. So if we know some bound for the second derivative, we can say that we can bound this error of our differentiation by this amount, and of course we will divide by h. So f tag is f of x plus h minus f of x over h with this error, and this error scales with h as one order of h. Yes, it's all of h, and it is a large error that goes with h, and always we want to somehow decrease this error as much as we can. Okay, any question? Okay, so if we use one another point, for example, we use f of x and f of x plus h and f of x plus 2h. And we want to evaluate the function or to approximate the derivative of the function at the point x. How can we do that? We have now 3 points. F of x plus h. We have f of x, f of x plus h, f of x plus 2h. And you know why we have these. For example, why we do this differentiation numerically. This function f, for example, we measured it, so we cannot measure it continuously, or that we somehow evaluated it in these points in some or with some complicated process for acquiring the data. Okay, so we don't know f continuously, we know it sampled in these points. So how can we use these 3 points? First, we can use these 2. Okay, that's how we use these 2 points. But if I have another piece of information, how can this help me for f of x? What do you suggest? I don't expect the answer immediately, but what do you suggest? Yeah.
We can take the derivative between fx plus 2h and fx and evaluate the function at fx plus h. So like average the.
Okay, so that's an attempt of improving, and we don't know if it doesn't improve or not. Okay, but I want some. If this goes like O of h, I say that this can help me to decrease this term. So I don't know. I don't want from you the answer immediately. But what do you suggest for me to do now, in order to get an approximation for the derivative? First of all, yes, what to do?
Expand it.
Expand it, yes. So I don't want you to see the answer. Let's go right here. So expand this, and expand this. Okay. So only look at the first and the third. Okay. So expand it. And with this expansion, you see that somehow I can also make this term cancel out. You know, at the end of the process, I will divide by h. So what was with f of x plus h and f of x, I took the subtraction and divided by h, and the error went like O. Okay, now I can use this and this to cancel f double prime. How can I cancel this with this? It's f of x plus 2h minus 4 of this, and this will cancel out. Okay, but when I take this minus 4 of this, I now have some thing for f tab. It's not 0, so 2h minus 4h. It's minus 2h f tab. Okay, it's good. It's not 0. But now I have f of x minus 4 f of x. So I have minus 3 of f of x. So I correct this, plus 3 of x. And then divide all of this by minus 2h, because this minus 4 of this is minus 2h f tab. So my formula for this approximation will be this. Okay. So it's 4 f of x plus h minus f of x plus 2h minus 3 f of x divided by 2h. This will be f prime of f tag of x, and an error that goes like, or goes as, h squared. Okay, that's how we put it. Now, there's something wrong here with this expansion. They say that this minus this is immediately minus 4h cubed divided by 6. It's not true. Why? Okay, it's true if you continue this series, but if you don't continue the series, if this is the error and this is the error, so this is at some psi between x and x plus h, and this is another psi between x and x plus 2h. Okay, so you have somehow to use theorems in order to bound your error, but we know that our error will be bounded by some number multiplied by h squared. Okay. And if you remember, when we used f of x plus h and f of x minus h in order to evaluate the derivative of the function, we also got O of h because of the symmetry. Okay, so we can use also these three in order to evaluate the derivative at this point. We can use these two in order to evaluate the derivative at this point with an error of h squared, or scaled by this. Okay. And how do we find high order derivatives? It's the same. So always we take a number of points, we expand them up to some high derivative term and make some combination or some linear combination between them such that all the terms that we don't care of cancel each other, and we are left with the term that we want and an error. So for example, I can use these two and combine them not with a minus but with a plus, and then I will get this, and I have to subtract minus 2 f of x, and then I will get f double prime. Okay. Any question? Okay. And if we think about the total error, you remember that when we take very small h, we have another problem, not only the truncation error that we got. The error that we got right now was the truncation. It was an error because we neglected high order powers of the function when we expanded it as a polynomial. And if h is so small, then f of, when we evaluate, for example, f of x plus h and f of x, they will be so close to each other. Yes. So when they are close to each other, we know that now the round of error will be important. It cannot be neglected. And how in the derivative, for example, of f of x plus h minus f of x divided by h, how does the round of error affect this? The error goes like what? It goes like the round of error of the machine. It's the value of f x plus h minus the value of f at x. So it's somehow the subtraction between two round of errors divided by h. So it goes like h to the minus. Okay. And we search an optimal h. And again, the truncation error is this. We have found that, and the round of error is delta epsilon m divided by over h. And if we demand that the derivative of epsilon total is 0, we get h optimal like this. And again, we don't know exactly what it is, what psi is, because we change the h, and for every h there is another psi, and this psi depends on x and h and the function, of course. But again, as we said before, I can take the maximum value here and try to get an approximation for this h optimum and check my h. If I get some h here, I can again make this iteratively, or that I can say it is sufficient for me. This h optimal gives me something good. We'll see an example. Okay. Okay, let's see an example. So here the function is so okay, nothing. We can say. Okay. So the function is the sine of x cubed. And the cubing is for the sine itself, not x. And we know that its derivative is 3 sine x squared cosine x. Okay. And we can find the maximum of the second derivative of it, and the maximum of the second derivative of it is this. Okay. So we can compute it. And we try the dx here is the h. Okay, and we try to make this symmetric differentiation f of x plus h minus f of x minus h divided by 2h. And okay, so everything here we talked about it. And we try the h optimal to be what we said. And this 10 to the minus 16, what's this? Yes, that's the machine rounding error. And we try with many h's. Okay, we try it with many h's, and that's what we get. So if we plot the theoretical error, what's the theoretical error? What's the meaning of this theoretical error? The theoretical error is f tag of x minus our approximation, f numerical. So what is this? This is f of x plus h minus f of x minus h divided by 2h. Okay? So that's the theoretical value of the error. Okay? And the numerical error is like this. It's so close. Okay? But it's minimal somewhere here. If we calculate h optimal as we calculated it, it will be here, the h optimal. So it's good enough. There is a better h. Yes, for example, this h here is better. You see? And this h here is better. It's the best one, the h here. Okay? But the h optimal that we calculated is sufficient, or it's good enough. And you see that when h goes down, somewhere we will get a minimal value of this error. Why? Because when h goes down, the round off error will be bigger and bigger. Okay, larger and larger. Okay. Any questions? Okay. So that's on differentiation. So it's always good somehow to start with somehow a big h and then decrease it. Okay. And numerical integration. So we'll talk about the numerical integration also in the next recitation. So again, we have a function, and either that we have it, but we don't know how to make the integral, or that the integral or the antiderivative function cannot be written as a composition of elementary functions that you know, or that we don't know what f is. We measure it in some sample points, or that we calculate it in some complicated way, and acquire a big grid of data, or table of data, but we don't know it exactly continuous at every point. And we want somehow to evaluate or calculate the area underneath the function, which is the integral. And the question is, how can we do it with minimal error, or with minimal error rate? When we talk about the rate in terms of the power of h, of the order of. Okay, so this area is the known Riemann method for calculating the area. So what's the Riemann method here? What's the difference between Riemann method here and Riemann method here? Both of them are Riemannian. But what's the difference?
Here you take the lower point.
Yes.
And here you take.
Yeah. Now here I take, for example, if I call the segments, if I call the points x0 up to xn. So the first one is the sum of delta x multiplied by f of xi, and I goes from 0 to n minus 1. That's the first one. And the second one is I goes from 0 to n minus 1, delta x multiplied by this. Okay. And we can use the point in between, but this is not the data that I get. But again, this can be Riemannian also. So f of xi plus 1 divided by 2, and from 1 to n minus. But this does not use the data that I have. Okay. Another way of calculating this integral, but it is not Riemannian way. What could it be? Not like this.
The area of the trapezoid.
A trapezoid, which is the sum of these two over 2. Yes. So the limit of this will be the integral if it converges. Okay. And the limit of this will be the integral. So the sum of them over 2 also will be the integral. This is the trapezoidal way, and we'll see that the difference between them is how fast this goes to the integral. Okay, so both of them converge to the integral, but how fast do they converge? Okay, so this is the trapezoidal method. So I take for each point the sum of the two values of the function. Again, it's not the function evaluated and the average between them. It's also true. Okay, the limit of this is also the integral. But with the data that we have, we take the average of these two sums. And we start our examination with only one little segment of length of h. Okay, so x1, x2, or x0, x1. Okay. And the question is now about the error. So how can we know what the error is? Again, we expand by Taylor series. And of course, here again, there is something wrong with what's written, but it can be corrected. Okay, so if we make the permutation here, so this will be F0 prime at what? At some sign which depends on x. Okay, so we have, for example, the I exact is the integral of f of x. We can think about it from 0 to h, because always we can move the x-axis. Okay? So we think about functions now, f of x from 0 to h. And this will be the integral f at 0 plus h f prime at 0 plus h squared f prime at psi of x dx. Okay, that's the integral in some exact way, and we have to say what's this psi. Okay, it's a fine such that this will be f of x. Okay, but we know that this psi of x is between 0 and h, and we can somehow call this another function.
It's supposed to be x, not h.
Huh?
No,
Hmm?
it's supposed to be x, not h.
Yes. Yes. Yeah. Thank you. So the integral over this will be h f of 0 plus h squared over 2 f prime of 0 and plus sum. What's the integral over this? Well, I don't know what's this. Okay, here we can use the mean value, the theorem, and we can say it's some value 0 and h squared and prime at psi at this value. Okay. Again, I can say that it is bounded by h squared over 2 and the maximal value of f prime at this segment. Okay, so what's written here is not so exact, but it can be corrected. And again, we don't do this much in this course. This is sufficient for us, but I have to say that. Well, I have to say. So the error will be scaled as h cubed, and that's why. Okay, because we make this integration, and this will be x cubed, and the answer of the integration is this of the exact. And when we do the trapezoidal method, we do h over 2 f of 0 plus f of h, which is what? It is h over 2 f of 0 plus f of 0 plus h f prime at 0 and something that goes like h squared. Okay, so our calculation or our numerical approximation of the integral will be this, while the integral itself is something like this, and the difference between them is only in this term. So the error will be of order h cubed. Okay, of order 3. Any question? Okay. So the Riemannian method will be of order what? Of order h squared, the Riemannian. But the trapezoidal is goes like h cubed. And if we want now, of course, before that, this way of trapezoidal will be exact if the function is linear. Yes, you know, if the function is linear, so the trapezoid is exactly the function itself, so it will be exact. And we can see that this is true because for linear functions, this term is 0. So the error is 0. The truncation error is 0. Okay. It's bounded by 0. Okay. And now if we have a range of x's, we have this range and divide it to many h's. And we want to calculate this. Okay. So how would the error scale? Okay. The answer is we take each segment. Okay, that each segment we take it with the trapezoidal method. So it's half over f of x I plus x f of x I plus 1. So every point, every intermediate point, not the end points, every intermediate point will be with the left trapezoidal and will be with the right trapezoidal, so it will be calculated twice. Therefore, the answer is the end points, the sum of them, and the sum divided by 2, and then the sum of other points. Okay, because these other points are calculated twice, from the left once and from the right. And we add the truncation error, which will be of order h squared, and the sum of this is the sum of the second derivative at some point xi where xi always some xi for each I is some point between xi and xi plus. This error, does it go like h squared, h cubed or not? No. Why?
Because you're summing over 1 over h
Yes.
values.
Yes. So this n is 1 over h. Okay, it's of order 1 over h. So when we see h cubed sum over all these points, okay, so this sum will be, so this would be h squared xn minus x0 over n, and this sum. And now this sum over n, I can say that there exists some psi between x0 and xn that gives me this m. Okay. Any question? Okay, we can say that this is the the intermediate value theorem n minus 1 times. Okay. So here we have an example. Let's use. So the answer of this integral, we know it, it's arctangents, okay? And it's arctangents 2. And if we want to use this trapezoidal method with n equals 2, which means we divide the segment or the range of integration into 2 segments, which are from 0 to 1 and from 1 to 2. So h is 1. And we use the values at 0, 1, 2. So the trapezoidal method will be the first trapezoid and the second trapezoid. Okay, the answer will be 1.20, where whereas the real answer is, or the exact answer is 1.107. I said 1.2, it's 1.10. So the error is 0.0071. Okay. Okay, that's what we said right now. That the error goes like h squared. And when we say that it goes like h squared, we can alternatively say that it goes like 1 over n squared. Okay, the number of the points or the number of the segments that we take. Okay, and why is it so important? Because when we want, if I want my error of the answer to be some value, for example, 10 to the minus 10 or 10 to the minus 8, and I get some value, I can decrease it by making h bigger, and I know how much I have to make it bigger. So if it's like h squared, maybe I will take it take h to be 10 to be the 10th of the previous h because it's squared. But if it's linear, I had to take it, for example, 100. Okay. So this helps me to know how much to decrease the h in order for my error to meet the criteria that I want. So here is an example of this. How many intervals are needed in order to calculate this integral to the accuracy of a truncation or of 10 to the minus 10? Okay. So again, this scales like n squared. I can make another way of integration that scales like, for example, n to the 4th. Okay. And then my answer will be another answer. Okay. So it will be the square of this answer. So it's much better. So if it's now 40,000, it will be the square. So now our error goes like 1 over squared. And if we take this, what?
Square root.
Hmm?
Square root or square?
The square root, because n to the 4th. I said square? Square root. Okay. So we know this function, so we have to calculate its second derivative. It's 2 over 1 plus x cubed. And what's the maximum of this? What's the maximum of this function? 2 over 1 plus x cubed in this interval from 0 to 1, 2. Okay, so that's the maximum of f prime prime, the double prime. And then if I want the truncation error to be 10 to the minus 10, so I demand this, and I take the maximum of it, then I take the minimum n that I have to take. Okay, so for example, if you take 50,000 points, you will be sure that the error will be smaller than 10 to the minus. Okay, any question? Okay, I think now we should take a break. I'm going too fast, I don't know. So let's take a break now for 10 minutes. Okay. And now we'll talk about the recursive trapezoidal method. So we talked about the trapezoidal method and then the composite trapezoidal method. So when we take more than one segment of length of h, which is a small length, And now we'll ask if I have some, not if I will build a method that can be calculated recursively in order to reduce the error of my approximation of the integration of the integral. And my method is like this. It's so easy. It says that at the zeroth order, I use only these points, the end points, okay, as sampling points. So here we assume that we have a function somehow analytically. We don't have only one sample of that one. We don't have a data of sampling. We can sample it. Okay? We are not restricted. So we know the functions. We can sample it, but we don't know how to integrate it. So to integrate it, we integrate over it. So we do this numerically. So at the first step or at the 0th step, I only use these 2 points. And then after that, at the second step, I use also the point in the middle. And after that, I calculated for these points and I add these 2 points. Okay. And after that, I calculated the integral or the approximation of the integral using these points, and now I add these points. Okay. So what's the motivation of this statement that I calculated this and I only add something? What's the motivation of this? The motivation is the formula itself. Okay, the formula for composite trapezoidal rule says that you have to take the endpoints, okay, and then you have only to take the sum of the function at the intermediate point. Okay, the evaluation of the function at these points. So if you want to decrease your h by a factor of 2, okay, so your integration, take it somehow by a factor of 2. We'll talk about it. Okay, and then add points. Okay, so you can use this answer, make some manipulation for it, and then add somehow the contribution of these new points. And with this, your truncation error will be decreased. Okay, because your h now is smaller by 2. Okay, so that's n0, and that's n1, that's n2, and that's n equals 3. And if we ask how many points we use at each n, so how many segments at each n we have? Here, 1 segment, 2. Therefore, how many total points taken for the integration? N total is what?
2 to the n plus 1.
Yes, 2 to the n plus 1. Okay. And in each step, how many new points do I have? So here we have 1 new point, 2 new points, 1, 2, 3, 4 points. So it is 2 to the n minus 1, and we don't, this is for n bigger than 0. Okay. So this is the number of evaluations I have to make with my n step. Okay. But let's see the formula or the recursive formula. So you see that these points are which points? Okay. If let's also say what is h n. H at the step n, it is the xn minus x0, or let's say b minus a, if this is a and this is b, b minus a over s, which is 2 to the n. Okay. And these new points are, which points are they? How can you tell me what these points are? So x, which x's are these? If I have this to be x, x0. Let's see what's a and b. Okay, this is a, this is a, and this is b. So what is this point? It is a plus h n. That's it. Okay. And what's this point? 3. And this? 5. So the points here are a plus 2i minus 1 h n. And I goes from where to where? I goes from 1. I goes from 1 to
And small.
n. Okay. And I have to evaluate the function at these points. So that's the thing that I will add somehow. Okay. We'll see now the proof of it, but we should also see this way. Okay. Okay. So and when you it's important now when you make this recursively in the computer with Python, you should somehow do this calculation, what we see here. You should do it outside the loop and check for the first 2 or 3 or 4 steps that your error is decreasing. And then you use the loop, because if you have some error and your error does not decrease or converge, you may stuck with an overflow, and your computer will get stuck. So if your code is not true and the error doesn't go to the criteria that you demanded, you may face or you might face overflow. Okay, so Rn, the evaluation or the approximation of the integral, if we use all of these points at some end step, is like this. Okay, so that's the trapezoidal method. That's our integration method with the trapezoidal rule. And if we use the Rn minus 1, we get this. And of course, Hn minus 1 is Hn multiplied by 2. Okay. So therefore, if now I want to relate Rn to Rn minus 1, what do? I make this, I divide this sum to 2 sums. One is over the odd numbers and the odd i's, and one is for the even. Okay, so this summation, I can take it with even and with odd. And of course, now the I goes from 1 not to, let's see, here it's an error. Here we have hn, not hn plus 1, okay? This is hn. And if I want to make this sum to the 2 to the n minus 1, I have to take the even numbers from 2 to the n minus 2. Okay. Therefore, the half of this is 2 to the n minus 1 minus 1. Okay. And this is also, I take the plus 1 because 2i minus 1, when I take this, will be 2 to the n minus 1, which is this. Okay. So you can make sure of this dividing for the sum that it's true. And now, and the hn, I wrote it as hn minus 1 over 2. And this thing, as you know, is this thing multiplied by this is r at n minus 1. So you see, and then we add these points. Okay, here, these points. So we see that when you use the integration, when we use the previous step, you don't correct it by some term. No, you multiply it by half and add a collection. Okay, and this will decrease your error. Okay, so it's not a mere adding or correcting. It's multiplying by half and then adding this term. So that's the way that we know how much we have to add points. At each step, I can calculate the difference between Rn minus 1 and Rn and see if I converge to something. Okay, so that's the error that I can check because I don't know the real answer of the integral. Okay, but I know that now I am converging more fast, and my way to check my error is to see that Rn minus 1 is decreasing smaller and smaller. Any question? Okay, and this is somehow an introduction for the next recitation, in which we will talk about designing some methods for clever integration with small error. So this Simpson way says this. So in the trapezoidal way, in the Riemannian method, we used 1 point, f of xi, for example, and multiplied it. Okay. So it's somehow, in some way, we can say that we approximated the function at that segment to be constant. In the trapezoidal way, we took the trapezoid. Yes? So we can say that we approximated the function at that segment to be linear. Okay, so we can go further. We can say that maybe if I take 3 points, not 1 point, 3 points for each segment, I can somehow approximate the function there to be quadratic. And this might improve my or my rate of convergence. But the question to be asked is, which points do I have to take, and what are their weights in this in my calculation of the integral? Okay. So I'm telling you that you take the point and the middle point between them, and this weights you should take. Okay, so now you don't know why did I choose these weights, but you have to take these weights. Third, fourth, third. Okay. And I claim for you, or I claim before you, that the error will be like this. Okay. Now, can you give me this way of integration? Yes, if I tell you that you should use x0 and x2 and the middle one between them, if I tell you that this, you can use what? Taylor expansion and find this third, four thirds, and third. Okay, you can find that these are the optimal ones because we get everything cancel out, everything that we wanted to cancel out, it will be canceled out, and we are left with h to the 5. Well, h to the 5. And if we make a composition, then we add all these terms, okay, from A to B. So we now use x0, x1, x2, but we integrate from x0 to x2 and from x2 to x4, and we use between these pairs, we use that formula of Simpson. And then the error will be not like h to the 5th, but it's like h to the 4th, okay? Because one h here will be computed with this as some evaluation of the 4th derivative of the function. So that's how it looks like. Okay. So between these 2 points, I take some quadratic function. Between these 2 points, I take some quadratic function, and we don't say what's the function. We say immediately what's the integral over this function, and the answer is the integral over this function is h multiplied by this. Okay. And here is an example. If we take this with this Simpson rule, so we take the point 0, the point 1, and the point 2. You know what? But the example is for taking from 0 to half, and from half to 1, from 1 to 1.5, from 1.5 to 2, and this one will be computed using Simpson method, which means that h now is no. This will be, you see, here is h. Okay. Every integral of these will be taken with Simpson. Okay. So we are using the 0, the 0.25, 0.5, 0.75, etc. And our evaluation is this. Okay. So when we use it with h equals 1, the error is 0.03, and when we use it with h equals 0.25, the error is this, okay? And we expect it to be lesser than the one before by 1/4 to the 4. And it really is. Okay, so as I said, we are finished. Okay. I have to do something with it. Okay. So that's for today. And your exercise, your homework, some of it will be optional. You can do it. You can. Okay, see you.